Right, continuing with this series of videos. Sorry, there's a little bit of lag in the computer. Examining the whatever I'm doing. I'm playing physics videos, lectures, and attempting to argue that although they can in some ways quantify effects, they're really bad at describing causes. That kind of thing, generally speaking. So, continuing.
Today I want to discuss with you RC circuits. We already discussed RL circuits. Now we get RC circuits. I have here a battery with an EMF V0. And I have here a switch connecting to a capacitor. And here a resistor. And I close the loop. When I have the switch in this position, the capacitor is going to charge up. I get a current I going in this direction. If I call this point A here, and this point P, and this point S, to make sure that we're on the same wavelength, I will call the potential over the capacitor, I will call that.
So, it'd just be easier if you just put plus signs and minus signs, just to clarify, but the plus side is on the left and the minus is on the right of the capacitor. So the voltage is going the opposite direction of the current as usual, which doesn't make any sense, of course. Really doesn't make any sense. Yeah.
VA minus VP. The potential over the resistor is of course always I times R, is then V of P minus V of S. The question now is, what is the potential over the capacitor doing as a function of time, and what is the current doing as a function of time as I charge up this capacitor?
All kind of deducible as, well, obviously you're charging your capacitor, so, you know, first it's going to take a lot of current to charge, and then it's going to say, I'm full, and then it's going to say, no thank you, no more pressure can be mitigated, so we're done for now.
And your intuition will help you a great deal without any fancy differential equations. It is clear that at t equals 0, the capacitor is not charged. There is no charge on the capacitor. And it will take time to charge the capacitor. So at t equals 0, you expect that the potential over the capacitor is 0. If you make t a little larger than 0, you're going to charge up this capacitor, and so the potential over the capacitor will go up, and therefore the current will go down. And if you wait long enough, we call that infinitely long.
Well, initially the current goes up because it's charging, and then as it's charging, the current goes down. So he picks an arbitrary greater than 0, but it's the greater than 0 is very, you know, the current will be going up initially, and then it will go down.
That the capacitor will be fully charged. It will have the potential V0 of the battery, and then the current has become 0. No current is flowing anymore if the capacitor is fully charged.
So, I mean, it's not a very good diagram, right? 0, down, 0. You know, I mean, it has to have it up first before it can go down. Gravity thing.
And so this capacitor is going to charge up, this becomes positive, and this becomes negative. And so you can construct a plot whereby you plot as a function of time here the potential over the capacitor. We haven't used any differential equations yet. You know that if you wait long enough, you will reach that value V0, and it's going to build up like this, asymptotically reach that value. And if C is very large, then the curve will be more like this. And if C is very small, then it will go much faster, of course.
So I would just argue that the V0 thing is sort of deceptive in the sense that the voltage doesn't go to nothing. It's just that the circuit is no longer charging, but obviously now the capacitor has voltage across it. It has a potential.
Small c. The current, as a function of time, In the beginning, the current will be high, but ultimately the current will die down when the capacitor is fully charged. So you expect something like this. So this you can do without any differential equations.
Yes.
Let's now do it the correct way. The closed loop integral of E dot dl happens to be...
I mean, the correct way. I think the correct way is to just understand that the voltage and the current are real things. I mean, it's a real change that's happening across the wire, potential change, that the capacitor stores the potential, and that there's some limit to how much potential the capacitor can store. I think that's I think that's the right way.
Zero, which will make Mr. Kirchhoff very happy. Closed loop integral of E dot dl in this circuit is zero. Mr. Faraday is happy and Mr. Kirchhoff is happy. There is no magnetic flux change here. We don't have self-inductances. The electric field...
We don't have anything producing a magnetic field, essentially. No, there's nothing in the circuit that has that's creating a disturbance in the environment of the entire circuit.
Inside the capacitor is in this direction, from plus to minus. The electric field in the resistor is in this direction. The current is flowing in this direction. And this battery, which has this as the positive side and this as the negative side, inside the battery, the electric field is in this direction. So if I start at point A, and I go around the circuit, then E and dl are in the same direction if I go from A to P. And so I get plus V of C, that's the E dot dl from A to P. Then I go through the resistor, again E and dl are in the same direction, so I get plus I times R. Then I come through the battery. Now the electric field is opposing the direction in which I go, so I get minus V0, and that is 0. So that's my differential equation, and I can write it differently because I know that I, the current, is dq dt, Q being the charge on the capacitor, and it's only if that number changes, if the capacitor is either charging up or discharging, is there a current flowing. And in addition, I know that V of C is Q divided by C. That's the definition of capacitance. And so I can write down for this V of C, I can write down Q divided by C. For I can write down dq dt, so I get R times dq dt minus V0 equals 0. And this is a differential equation in Q. We've seen an identical differential equation. It was not in Q, it was in I, but it had, of course, a completely similar solution. And the solution to this differential equation is actually quite simple. I will put it on this board. Q, so this is going to be Q as a function of time, is V0C times 1 minus E to the minus T over RC. If I take the derivative of this Q, then I have I, because I is dq dt. So I, which is dq dt, then becomes V0 times C. I get a minus sign. I get another minus sign. Then I get 1 over RC. And then I get E to the minus T divided by RC. So the two
doesn't seem very simple to me, but whatever. Seems like it gets more complicated rather than simpler, but whatever.
minus signs eat each other up. And I lose one C here. And so I get that the current as a function of time is V0 divided by R times E to the minus T divided by RC. So that's the curve at the bottom. And the potential over the capacitor is now very simple, because the potential over the capacitor is Q divided by C. And I already have Q here, so I simply have to divide this C out. So I get V0 times 1 minus E to the minus T over RC. And so that is the upper curve. And so we can now make a small table, and we can look at various values for T. Maybe I should do that here on the blackboard, because I don't want to erase anything yet.
So anyway, yeah, sorry, this just isn't great material for conversation. It's just a bunch of... I think it's made it more complicated than it needs to be, in the sense that obviously we know that there's time involved, and that the capacitor has a certain speed at which it can charge up, and that there's a certain capacity it can charge up to, and but I don't know if there's more to say.
So we have t here, we have I, and we have v of c. And when t is 0, you go to the equation of I, so this is 1, so you have a current v0 divided by r. And your vc of c is 0. That if t is 0, you get 1 minus 1. Oh, sorry, I have to go here. You get 1 minus 1, so you see indeed that the potential over the capacitance is still 0. If you wait long enough, then the current must go to 0. That exponential function goes to 0, if you wait long enough. And your potential over the capacitance then reaches V0, which is exactly consistent with our solution. If you wait a time RC, that's called the time constant of this circuit. In the case of the current, it's also called the decay time of the circuit. Then, of course, your current is 1 over E times V0 divided by R. And 1 over E is a roughly 0.37. So your current is down to 37% of what it was at the beginning. And after a time RC, the potential over the capacitor is 1 minus 1 over E times V0. And that is then about 0.63. 63. 0.63, 63%. In other words, if I go back here to my plot, and if I draw a line at time RC, then this value here is 37%.
Yeah, I don't know exactly how he's RCing, but I guess that's a combination of the capacitor and the resistance, which will tell you. Yeah, I don't know. It has something to do with how fast it charges, but I don't know exactly what RC is.
Of the maximum, and this value here is then 63% of the maximum. So the solution is rather obvious, very intuitive. And the RC times can vary an enormous amount, as you can imagine, depending upon the values for R and C. If we have here an R and a C and we want to know what the RC time is, convince yourself that the product of R and C indeed has units of seconds. Remember, we had L over R before, which has also units of seconds. RC also has units of seconds. If you have R equals 1 ohm and C is 1 microfarad, then the RC time is only a microsecond.
So the farad is telling you how much surface there is to put charge on, and the R is the resistance in the circuit, and so obviously those two things would combine to tell you how long it'll take to charge the capacitor. How much capacitor you have and how much resistance is in the circuit will tell you how long it'll take to charge. Yes.
But if you have R equals 100 mega ohms and you have this 1 millifarad, then this is 10 to the 5 seconds, which is longer than a day. And that would mean that it would take you even 3 days to reach 95% of V0.
Well, he's put a huge resistance in and a gigantic capacity. So obviously, yes, it would take a long time to fully charge the capacitor. And the important part is that the voltage on the capacitor is the density of the charge you've put on it. So you could be putting a high voltage on the capacitor, but if you're only putting a tiny bit of it, it will be diminished because it's distributed so shallowly.
After 3 days, you would still have only 95% of the potential difference of the capacitor of the maximum value that you can get. Now what I want to do is I make a change here. I have here a conducting wire. I call this position 1 of the switch, and I'm going to put the switch in this position, position 2. And I can do that without any danger. Remember, I waited until this capacitor was fully charged. There was no current running. And so when no current was running, I can quietly take the switch and put it in this position. Of course, this side is positively charged and this is negatively charged. So now you're going to get a current which is going to run counterclockwise in opposite direction. And what it
So he's just disconnected everything on that side. So even though he just took out the switch takes out the battery. So now he's just closing the circuit between the capacitors. So now the capacitor is the battery, and the battery is just going to be shorted essentially through the resistor. And so it's just going to work like a battery, and it's going to run out, and that'll be it.
what's going to happen is the capacitor is discharging now, and the resistor will dissipate the energy that is in the capacitor. The 1/2 CV squared energy stored in the capacitor is going to be dissipated in the resistor in terms of I square R, in terms of heat. And if you wait long enough, the current will become 0. So it should be obvious what's going to happen. If I return to this curve here, if I redefine my time equals 0, and if this is the moment that I put the switch in position 2, then I expect that the capacitor will discharge. You get a curve like this, and I expect that the current, which now becomes negative, it reverses direction, and I call that negative, and so the current will come like this. And if you wait long enough, of course, the current will again become 0. You have discharged the capacitor.
Well, I don't see any point in making it a negative because it's really not a negative current. But whatever, it's just another line like this. I mean, the current will be high at first, and then it'll drop off as the capacitor runs out of juice.
So if you want the formal solution, you have to go back to the differential equation, and you take this term out because it's not there. And now you have to solve this differential equation again, which is now utterly trivial. And I would like you to solve that differential equation. You couldn't have an easier one. I will give you the solution to I as a function of time, and you then will come up with this part. I as a function of time is exactly the same as this, except there's a minus sign, provided that I call this t equals 0. So I redefine the 0 time. And so I as a function of time is the equation that you have here, but now with a minus sign. So you get an exponential change again, but the current has flipped over.
You really can't have a minus sign on a, there's just no point in minus current. It just doesn't make much sense. Current's always positive value. Whatever.
I can demonstrate this to you. I have a electronic switch, so I go between 1 and 2. Every 4 milliseconds I throw the switch. And so what I have is, as a function of time, what we call a square wave. So this is my battery. And this time here, from here to here, is 8 milliseconds. This is time. And so this is that value V0. And the values that I have chosen for R and C, I will give them to you. The value for V0 here is 1 volt, and here of course it's 0. The value that I've chosen for R is 6 kilo ohms, and the value I have for C, I think is 0.1 microfarad. Yes, that's what it is. And there's a reason why I've chosen these values.
So 6,000 ohms, is significant enough resistance.
This is 0.1 microfarad. And so the RC time is 6 times 10 to the minus 4 seconds. It's 0.6.
It'd be nice to have it in milliseconds. Let's see, 0.6 milliseconds.
Milliseconds.
Okay.
Which is substantially smaller than 4. And so you can expect that the capacitor becomes almost fully charged in this 4 milliseconds. That's why I chose the RC time substantially smaller than 4 milliseconds. And my setup is such that I can show you the driving voltage of the battery. I can show you this. I can show you then how the capacitor is charged and how the capacitor is discharged with the time constant RC, and also how the current goes through the system. So I can show you also this curve. And then I can change the capacitor so that the RC time changes. I can also change the resistance. So let me change first the lights so that you get high quality for your money. You already see there the switching voltage between 1 volt and 0. And now I'm going to show you the voltage over the capacitor, and I will take the other one out. Here you see indeed exactly the image that we discussed. So you see early on the charging of the capacitor, and it reaches effectively the maximum value. You know, you don't have to wait infinitely long. That's always, we say infinitely long, but that's clearly if you wait 3 or 4, 5 times RC, then you're almost there. And then here, I'm going to switch it back to position 2, and you see it's discharging. And then it's charging up again and discharging. And now I can also show you the current.
So just a little thing. So the idea is that when the capacitor is charging, you just think of it as almost like spray paint. You know, you're putting charge on a surface, and it becomes, as you get more and more stuff on the surface, the amount of little spots left to put stuff on becomes smaller and harder to find almost. So in a sense, the charging isn't an absolute thing. Like, it doesn't just completely charge. It takes some time for every little bit to get filled in. Yeah, I'm just trying, it's a conductor, so it should do it fairly well, but I mean, there is some limit to how perfect the charge can be. There can be spots that are isolated, or, you know, blah blah blah, and, you know, those can charge slower or whatever. I mean, just the dirt in the substance, different little factors that can prevent it from being completely charged. So if you just keep the pressure on, then little bits can seep in now and then, technically. The longer you leave it connected to a battery, the more certain you are its charge will be complete.
On the same plot, as the battery, as the capacitor is charging, you see the current is high. But by the time that the capacitor is fully charged, the current is 0. But the moment that I throw the switch to position 2, the current flips direction, becomes negative, and then as the capacitor discharges, and heat is dissipated in the...
So again, the current can't be positive and negative. It's just, I think it's a silly way to look at it. Current is essentially the volume, and the voltage is the thing that has the directionality, and there's no point in confusing things by giving current directionality. Current has to be going in the direction of the voltage, so I don't know why they did this current goes backwards crap, but it's kind of crappy.
Ultimately, the current again will become 0. What I can do now is to increase my capacitance by, for instance, a factor of 5. So that would change my RC time to 3 milliseconds. So now there is no way that the capacitor can become fully charged in the 4 milliseconds that it has. And you will see that indeed, if I make this 0.5 microfarad, then you see that the capacitor has not enough time to get fully charged. And so here you begin to discharge. Notice also that the current doesn't reach the 0, for the same reason that the capacitor doesn't get fully charged. So it never reaches the point that the current becomes 0. I'm already switching.
You're not draining the capacitor because the frequency is higher than the capacity of the capacitor to fully charge and fully discharge. So this is why capacitors are used to get rid of noise, signal noise. It's because if the noise is faster than the capacity of the capacitor to absorb it, then it just kind of kills it.
Here to position 2, and the current then flips over, but never becomes 0. All right, so let's go back to 0.1 value. There it is. This is easier than LR circuits for the reason that we don't have to deal with Faraday's law. We don't have a non-conservative field, and so it's easier to imagine things because we're dealing with Kirchhoff's law, so potential differences are uniquely defined and don't depend on the path.
So all this stuff comes up with Kirchhoff and his opposition to using it, so he's talking kind of nicely about it now and just pointing out how, yes, in all these other circuits, this Kirchhoff's rule works perfectly fine, and the only one it doesn't work perfectly fine in, and I don't think anything works perfectly fine in, is when you end up with an inductance, something radiating force in the middle of your circuit. Yeah. Because there's going to be vagaries to how much it's going to affect the other parts based on proximity and composition and all that crap.
With Faraday's law, they do depend on the path.
I mean, I found that just working on circuits. I did some of that in my youth, And you found that all you needed to do was put a piece of foil over something else to shield it from what this other thing, the little other thing, was creating some radiation. And you just, some other part was sensitive to the radiation. You just put a little piece of foil and ground it, and create a shield against it.
So now I want to change to a different subject, which is transformers. Transformers play a very important role in our lives.
Run our economy. I just hate that phrase.
Transformers are key in many instruments that you use at home, but also key in getting the energy all the way from the power station to us, as you will see. A full understanding of transformers is not easy. It's extremely complicated. It's really more like an engineering problem than a physics problem. I will give you a simplified version in which I leave a lot of details out, but the basic idea will be there.
Yeah, I don't know. I don't think he really does deal with a lot of the eddy current stuff and all the rest of it that, I'm not convinced has anything to do with anything. But anyway, it's just a transmission of the pressure that you're exchanging and how efficiently you can do that. So using different plates of pieces of metal with more surfaces and all that kind of stuff makes a difference. It makes a difference for a reason, blah, blah, blah.
Here I have a coil, and I call this coil the primary.
Alright, let's understand. The coil's only creating a strong field inside. Okay, outside nothing, inside everything. It's inside, it's all being reflected.
This coil has N1 windings and has a self-inductance L1. And I put here a voltmeter, which I call V1. It's always in that circuit. And the current I1 is running through the coil and returning. And there is a teeny weeny little current I1, I put a little I there, running through this voltmeter. Insignificantly small. So I just call this also I1, because this I1 is so small. But it allows me to always monitor V1. So that's the primary. Now we have a secondary, which is wound in such a way that there is a magnetic flux coupling between the two. This is the secondary.
So you can couple them in different ways. You can couple them with metal, okay, or you can couple them by having them wrap around each other, and then one is going to feel the reflections of the other. Feel, tricky word.
It has N1 and 2 windings. Self-inductance is L2. And I put here a voltmeter V2. The current I2 is flowing here. This is I2. Here's the consumer. This is where you are, maybe. And I2 is flowing back through the coil. And here is this teeny weeny little current I2 flowing, so that I can monitor the value of V2. What I can do now is I can write down the closed loop integral of E dot dl for this closed circuit here. And I have to apply, of course, Faraday's law, because I now have a changing magnetic flux. They're always AC. Transformers always require alternating current. And so if I start here...
Are pulsed DC. So the tricky words here, I mean, it's interrupted voltage. Essentially, all you have to do is interrupt the voltage. You up and down, any kind of variation in the voltage. And so it's kind of a deceptive way to say it, because it's just the variation in the voltage that will dictate the fact that the magnetism is increasing or decreasing, and now the pressure can be increased and decreased. That is, you can push and then let relax and push and let relax, or you can go push and then go push the opposite way, pull, then push and then pull. So there's but both work. Push, stop, push works. Push, pull works even better.
here and I go through the self-inductor, I know there is no electric field in the self-inductor, so that contribution of E dot dl is 0. Then I arrive here at this current which is opposing me. I go in this direction that the E field is opposing me.